Hi everyone. So we now have all the elements to go and use the tools that we have learned about and derive the momentum equation, so the Navier-Stokes equation. Before we go that, I wanted to precise a few things about the Reynolds transport theorem. We have said that this theorem allows to actually relate the rate of change of an extensive property B, so mass, energy, momentum in a system, and you see here the system, it's a material volume of fixed identity. You also see that this is a moving system because we are using here the material derivative. And so this rate of change is given by the time rate of change, so partial derivative here of B in a control volume, and the net flow rate of B across the control surface. In the beginning, we have derived this for a fixed control volume in space and time, but then we also discussed that since at time t we have that the volume and the material volume and the control volume are one and the same, we can indeed evaluate the right hand side of this expression on the VMT and SMT. So the control volume at time t and the control surface at time t. And so we said that this is a generalization of the Leibniz formula in 3D. Now we can also do another thing, is that we can actually go from this formulation to this formulation by using the Gauss-Green theorem, the divergence theorem that allows to go from a surface integral to a volume integral. Something that I wanted to point out as well, the velocity here in both these formulations, so with the fixed control volume or with the moving control volume, is the absolute velocity of the flow. There are other formulations, I want you to be aware of that, of the Reynolds transport theorem that will employ the relative velocity. And so I just want to make sure that you understand this is the absolute velocity here. Okay, before we go on, I wanted to briefly remind you about the use of the Reynolds transport theorem. And so let's have a look again at the continuity equation. Again, we say that we use a material volume VMT that deforms with the flow, but it's never crossed by any mass flow. It means that the cross product between the normal to the surface and the velocity is equal to 0 on Sm. Okay? Now the mass principle here is quite easy. We just have to say that the dmm in the material volume in time is equal to 0. It's actually more appropriate to use the material derivative rather than the total derivative. And so what we have here is capital D mm, so m means material element, is equal to 0. And this mass here is simply the integral on the volume of rho dv. Okay, so now if I plug everything together, what I have is simply the integral over Vm t, then I have a d over dt here, rho dv, and now what I do here is that I apply the Reynolds transport theorem, so the one that we just have before in this page. Of course, here for the case under investigation, our B is equal to 1 because we have the transport of the extensive property, which is mass. So our B is equal to 1. So what I get here simply is that this is given by the integral over VMT d rho over dt plus divergence of rho v. Okay, and this is equal to 0. Excellent. So what we found is the continuity equation that we have already found in other different ways. And something that I wanted to point out is that if we have an incompressible flow, we get something which is of this kind. So the divergence of V equals 0 becomes the continuity equation for an incompressible flow, a flow for which the density is constant. Okay, having said that, we can actually move on and now tackle the momentum balance, momentum equation. Okay, now similarly to what we have said for the to the macroscopic balance of of momentum. In this case, when we look at the material volume VMT again, so that the forms it's never crossed by mass flow rates and so on. Of course, we look at the variation of the momentum, so the net rate, the momentum rate of change in this material volume, and of course, in differently from the mass balance, this will not be equal to zero because it will be equal to the sum of applied forces on the control volume. So in other words, when I write this, so d over dt, and here I have the integral over vmt of rho v times dv. Now my property b is the velocity. I put it here. Okay. Then this is not equal to zero, but it's equal to the forces which are applied on this, which are of course volume forces. So the gravity and surface forces. So here it's an integral on SMT. It's F ds. So here I'm using this line, underline, to indicate a vector again. Okay, great. So now we have to do some reasoning about these forces. So these forces F. But before we go there, I just want you to notice that this is nothing but Newton's law. Probably you have noticed that, but if you look at this equation, you realize that this is Newton's law. Okay, good. So let's discuss a little bit these surface forces. Now the surface forces, if you think about them, they should be a function of both the position on the surface and also on the orientation of the surface with respect to the force itself. Okay, so in other words, F should be a function of the position R and the normal to the surface. But to facilitate ourselves, the way we express that is as the scalar product between the normal and the tensor that only depends on the position on the surface. Now this can be also proved, but you can take it as it is. Can be proved by considering a tetrahedron and the forces which are acting on that, similarly to what we did for demonstrating that the pressure is a scalar. But now, for our purpose, let's consider that this is the way you express the force. Okay, once you have that and you plug it in the previous equation, then what you get is the following. You have d over dt, so the material derivative over this material element of my volume, of my momentum in the volume. And then this is, as I said, equal to the sum of applied forces, so gravity. And now what I have, it's a surface integral. But instead of having the force, I have the product, the scalar product between n and the tensor, okay, at t. And so this is a ds. Okay, now what I do here is that I apply here the divergence theorem. And I apply here the Reynolds transport theorem with the b, remember here is the velocity. Okay, and now when I do that, I get let's say the following. So I have so for the first part, yeah, so you apply the Reynolds transport theorem, I will have d rho v over dt. Okay, this is an integral over vmt. And I put a parenthesis here. Okay, then plus divergence of rho v. Okay, and I put this on the left hand side. I have minus rho g because it's still a volume integral, and this has become now the divergence of T, because it has become, with the divergence theorem, a volume integral, and dV. And this is equal to 0 now, okay? And then, of course, this should be valid at each and every point of the fluid, which basically means that I end up with my equation, which is d rho v over dt plus divergence of rho vv equal rho g plus divergence of t. Excellent. Now, something else I want to point out is that this term, if you use the definition of the material derivative, can be expressed as rho times dv over dt. Here we have introduced the material derivative, and so I invite you to actually try to demonstrate this equivalence. It's actually pretty easy to do. Now, if you look at this equation, so this is the equation that we will work on, and so this equation is also known under the name of Cauchy equation, and it's actually used in continuous mechanics very broadly. Now, the step that we need to go from this equation to the equation of the Navier-Stokes equation is to actually express somehow this stress tensor. And so this is what we are going to do in the following. So we will write here again the Cauchy equation so that we have it under our eyes. Okay. And then we take to study, so we want to study this tensor T. And so for doing that, we take first the case where the fluid is at rest, so there is no fluid flow. Okay, so static conditions. So in static conditions, which means V equals 0, we know that the only forces which act on the element are the pressure forces. And so in this case, it's very simple to actually stipulate that the tensor T should be equal to minus pressure times the identity matrix. So in other words, it would be a matrix of this kind, minus P, minus P, minus P, and all the other elements equal to 0. And if you look back at the Cauchy equation, under these conditions, you in fact get the following. You get that since so let's write everything. So you will get rho dv over dt, which is 0, because it's a fluid at rest, equal rho g plus divergence of t. Okay, and so now this becomes very simply rho g equal gradient of t, which, if you remember, this is Stevin law. Okay, so what is the conclusion of this first observation? The conclusion is that the stress tensor T should at least include a pressure contribution. Okay? Okay, this is very important. It means that if we now look at the dynamic conditions, so it means if you have a velocity vector which is different than 0, then in that case, so the tensor will include, of course, this pressure contribution that I bring to the left, so they become positive. And then they will be, and this is something that we are stipulating, a function of the gradient of velocity. Okay, so in dynamic condition, the fact that you will have a gradient of velocity, and this is something that we have already discussed when introducing the shear stress. This gradient of velocity will induce some shear stress forces uh, that will cause the instauration of some momentum diffusive flux. Okay, so we stipulate that this tensor in dynamic conditions will be a function of the gradient of velocity. So the existence of this gradient will be responsible of the forces that will apply on the fluid elements. You know very well that a gradient can, a gradient in this case is of course a matrix here, because it's the gradient of a velocity vector, and you know that you can decompose every matrix in a symmetric and antisymmetric part. So in this case, we would have that the symmetric part is 1/2 gradient V plus gradient V transpose, okay? While the antisymmetric part, so this is that, the antisymmetric part will be 1/2 gradient V minus gradient V transpose, okay? And so it's very simple to show that this symmetric part is responsible for a pure deformation, while the antisymmetric part is only responsible for what we call a rigid rotation. Okay? So it means that this function of the gradient B should be only proportional to the symmetric part of this gradient, not to the antisymmetric part, because the antisymmetric part is not responsible for shear, for strain. It's only responsible for a rotation. So in other words, what we postulate here, what we are postulating here, is that the tensor T, so in dynamic conditions again, the tensor T will have a pressure component that we already discussed, plus another component that will be only a function of the symmetric part, so of the strain rate of the velocity gradient. And of course we have introduced this coefficient here that you remember very well. This is the dynamic viscosity of the fluid. Okay? Okay, so we have the expression that we need for the stress tensor. Now we are able to actually rewrite our Cauchy equation. So that was this one. So Cauchy was rho dv over dt equal rho g plus divergence of t. We wrote it. You can write it in the following way that become so giving rise to what we call Navier-Stokes equations. So we write it like rho dv over dt equals minus gradient of p plus mu Laplacian of velocity plus rho g. Okay. In addition to that, of course, for an incompressible flow, so we are always in the case of an incompressible flow, we have to consider the conservation of mass. And so now we have a set of two equations. Actually, it's a scalar equation, this one, and then you have three uh, three equations that are associated to Navier-Stokes, because these are vectors, so you have three equations for that. So we have three Navier-Stokes equations, one continuity equation, and if you look at the problem, it is well posed because the unknowns that we have are the velocity and the density, while and the pressure, sorry, while the density and the viscosity are known from constitutive relationships. So in other words, so the unknowns here are the pressure and the velocity, while so the velocity here, while the density and the viscosity, so these are from constitutive relations, and the orange ones are unknowns. And this is also known. Okay, so it's a well-posed problem. We have enough equation to solve the Navier-Stokes equation. So we have enough equations to solve for the unknowns that we have. Okay, excellent. So you have seen how we can actually derive these equations. Um, you know, as I told you in the class, that there isn't to date a solution to the, I mean, a proof of the solution of the Navier-Stokes equation, although we already solved them numerically in computer simulations. And so we already have an idea of how these turbulent structures develop, but there isn't to date a theory that is associated to turbulence and that allows to prove that there is a smooth and an existing solution for the 3D Navier-Stokes equation. There are, of course, solutions that exist for specific cases, simplified cases, and these are things that we will see in the class together. But there isn't a general solution for them. Okay, so I think with that we have covered all the material that I was interested to share with you. I think you have now a lot of material um, to that actually represent for you a tool to approach and model and solve very complex problem. And so I think I was able to show you that by using complex mathematical tools, we are able to establish in a very efficient and also elegant way some conservation principles of properties such as mass and momentum. Of course, the same approach could have been used for the energy equation, and this is what you will do in the second part of this class. So bye.